platformization.
Say something.
הלו. תגיד לי. הלו.
I want to remind us all that in order to achieve the vision that Elisha is talking about, that Nir is talking about, that Yannick is talking about, that the company, the Wix is talking about over the last year, of turning ourselves into small building Lego blocks, okay, of functionality that we can assemble both internally whenever we're building the vertical, but also externally for Wix code users that want to use our amazing functionality and not only add in vertical. In order to achieve that, okay, we have platformization. We need to make sure that we expose everything we do, every new functionality that we build in APIs. Okay, again, both internally, so we don't redo the same effort again and again. We don't have 3 different chats or 3 different email providing services that have common components that we can use. Now, this is a process that starts with product. Okay, product route weights are guided to think in terms of API. Okay, an API first, not only product first, but API. What do we expose? What common use cases do we have? Which other verticals we know need and are going to use our functionality? And they're supposed to come up with a product that already defines the high-level functionality of our API. Okay? And then when it reaches us, it reaches development, then we need to finalize how this API looks like. And we need to do this together, or in a review, eventual review, together with the platformization team. Because what we're formalizing in the background are guidelines for standard APIs. Because we want the external developers and also ourselves to have different interfaces that makes common sense together. Okay, that we don't build things in silos. So in cases that this is what's already happening in your team, your product has already consulted with the platformization team, already brought the ideal API that they want to build. Excellent, but keep in mind that sometimes it doesn't happen. Okay, for some features, platformization was not part of the loop and was not part of the thinking process. And instead, you get just another feature or new functionality that you're requested to provide as part of your vertical. So this is when you need to raise a flag. Okay, if this is new functionality, this is not just a fed server-side wrapper that just wraps and combines two additional services. If there's actual new business logic that you're building, it needs to be platformized. Okay, it needs to have an API so others can reuse it. So please make sure that you keep that in mind. Okay, get the platformization team in the loop to make sure they review and provide their insights. Okay, otherwise we will never get to this level. Now, the other mental note I want us all to have is we're a year into platformization, which sounds like a long time, but it's really very, very early, very early stages. We have about 20 services that are currently already platformized. Cool. And the know what we're spreading out. So this is very early stages. So the processes are far from being effective around it. Okay, the communication is not yet effective. And the infrastructure is also still very young and we still have lots of issues. It's going to be still a long road of stabilization. It's going to be a long road of stabilization, but I want to make sure that everyone here is part of that. Still, I think we're checking the context switching and it's not very good. That's all. Be part, okay, of this stabilization. Be part of this learning process. If you have onboarded a platformized API and you felt that things are not going right, okay, both in terms of communication with the platformization team or the infrastructure being cumbersome, doesn't cover whatever you need, or the product being premature and not coming in with the relevant use cases, raise flags, road talks to your product, to your managers, to the platformization team, to us, because we want to make sure we continually improve the process. Make sense? Thank you. And Amir, you will introduce before even coming into the room. That's the first. That's the post fashion.
Hi, my name is Amir. What do you want to yeah, I've been like a Java full stack developer for 13 years or something, mostly in startups. I was involved in Code3 for 3.5 years now, and I just recently moved to the original new team, the Metasite Republic, and happy to join.
Room and say hi again. So, Dino, all hooked up?
Yep.
Anything else you wanted to share? Cool.
Okay, hello. Everybody hears? Yeah, cool. Hi everyone, I'm Dima. Those of you who are sitting in the back, if you can please like come closer to the screen, it will be much appreciated. Yeah. You don't have to, but you're welcome to. Thank you. Yeah. So the papers have been given to you. Just keep them for yourself for a while, and until the end of the presentation, you'll understand what it is, how to use it, and so let's start. Yeah. So today we're talking about Bitcoin, and it's pretty wide topic which can be attacked from very different angles, and it's very negotiable and debatable. So first of all, before we start, let's say a few words about what we're not gonna talk about today. So nothing about politics whatsoever.
So the Banco hack, not going to talk?
No, surprise, surprise. Nothing about economics, whether Bitcoin is a good solution, bad solution for like worldwide economics. Nothing about Forex, foreign exchange, how to make profits and stuff like this. Not today, so yeah. Advanced Bitcoin features like multi-signature, SegWit, Lightning networks, and many other topics not covered today. Ethereum, smart contracts, initial coin offerings, not today. And any more Litecoins, Doggy coins, and the general name for all of them is shitcoins. So yeah, not today. Today is core Bitcoin talk. So what is on the presentation today? So we're gonna dive into transactions, blocks, and blockchain, the main structure, data structures of the Bitcoin network. Then we're gonna say a few words about the network itself, how it works, and sum it up with keys, addresses, and wallets. So, but first of all, a few dry facts. So Bitcoin was invented in 2008 by mysterious Satoshi Nakamoto. Up until today, no one knows who he is. There are some few rumors, but no. First block ever mined in the blockchain, it's called also Genesis block, was mined on 3rd of January 2009. So this is the actual date where it all started. It's hosted on GitHub. The core implementation is written on C++. It's open source, by the way, under MIT license. And interesting fact, Bitcoin's current version is 0.16. It's still a beta version. Keep in mind, yeah. 21 million coins will be mined in total. Up until now, there are about 17 million mined already. And each Bitcoin is divisible to 100 million atomic units called Satoshis. It's like dollar and cents, so it's Bitcoin and Satoshi. Okay, so have a look at this Times magazine. It is from January 3rd, 2009. Remember this day, the first block was ever mined. So two interesting things on this Times magazine. So first of all, Israel, of course, enters Gaza again. But the more important and relevant thing is this one. This topic, Chancellor on brink of second bailout for banks. Why it's so interesting and related to Bitcoin? Because this is the sentence which was integrated into the first ever transaction in the first Genesis block mined on this date. This is how Satoshi Nakamoto actually proves that the block was really mined at this date and not before. I think it's quite cool. We're going to see it in a few more slides inside the first transaction.
Question?
Yeah.
Does he need to prove it, or it's just like
Yeah, it's a good question. So the question was, does he need to prove it, or it's like some?
Yeah, good.
Yeah. So he doesn't need to prove it technically, but in order to okay, there are always rumors about, well, maybe Satoshi has pre-mined some Bitcoins much before and has a huge advantage and has a huge amount of Bitcoins for himself. So no, the first block was really introduced on 3rd of January, and that's the proof. So yeah, this is the Bitcoin circulation graph. Overall, there were going to be 21 millions. Today we have around 70 million Bitcoins mined already. So again, what is Bitcoin? So we have a lot of words describing it, like buzzwords. It's decentralized, it's peer-to-peer, it's cryptographic. What does it even mean? It is digital, well, of course. The main point here is that Bitcoin, it's not a currency, it's a protocol. It's a payment protocol. So it's not a network, it's not a currency, it's not a coin, it's not an ecosystem, it's not a financial fundament, it's a protocol. Like HTTP, a bit more advanced. So the use case that Bitcoin proposes to solve is a standard one where Alice wants to pay Bob, but without any central authority, meaning without any central bank, any central server, any centralized provider like PayPal or something, and with no double spend, meaning when Alice pays Bob, Alice can't at the same time pay the same Bitcoins to Klo or Dima or anybody else. So now, let's dive in and let's start with transactions, blocks, and blockchains. So these are the main fundamental units of the Bitcoin. So first of all, what is what? We start with block number 0, which is also called Genesis block. And the first block mined in 2009 included a single transaction with amount of 50 Bitcoins, which went to the miner, to Satoshi Nakamoto himself. So the block has some header, some metadata, and this single transaction. Then later on, block number 1 was created. It contained few more transactions. By the way, pay attention more blocks and more blocks and more blocks. In each block, there is like blue transactions, a lot of transactions, up to 1,000 approximately. This can be a bit more, a bit less, but that's the normal number. And there is an orange transaction. What is orange transaction? It's the first transaction for a block. This is a special sort of transaction. It's called coin-based transaction. This is the transaction which gives the block miner, we don't know yet what miner means, but for now just think of it as a block creator. So the orange transaction is a reward to the block creator. And it's only one of it, one of this type in every block. Every block has it and only one. So yeah, many more blocks came up, and up until yesterday, well, yesterday was block number 531,527 was mined. Approximately every 10 minutes, a new block arrives. All those blocks is called blockchain. So in a nutshell, this is it. Thank you very much. Yeah, just kidding. So we just started. Okay, so that's the structures, that's the relations. All right, so let's dive in and have a look what transaction actually is. So we'll start from transactions, go to blocks, and then spread to blockchain itself. So transaction, you can think of it as sending money from one user to another user. But in a more precise way, I prefer to look at it as a paper check, like a bank check which you sign. There are a few reasons I prefer to look at this way. First of all, in a paper check, you have explicitly the payee, the person you are paying to, have the amount. You have a signature, your unique signature, which will be validated later on by the bank clerk. You have a date. From this date and forwards, the check can be handled. Prior to this date, it can't be. The same goes to Bitcoin transactions, by the way. You can create a transaction from now to 1 year to 2012 or like to immediate pay. Interesting thing, when you create a check, like bank check, and you sign it, money doesn't transfer yet. The actual transfer happens when you bring this check to a bank clerk. He validates all the information, the signature, approves the check, then transaction happens. Same goes in Bitcoin, by the way, meaning you can create a transaction, and up until it is included in a real block, which is added up to a blockchain, it's not valid.
So,
yeah.
So who is the clerk?
Yeah, the clerk is a miner.
A third miner.
What do you mean, a third?
Like, I want to transfer money to you, right? So
you are not a miner, I'm not a miner as well. There is some miner, lot of them basically. Each of them is a clerk.
So we might be miners, but this is irrelevant to
yeah.
Okay.
We will come up to it. Okay, so this one is a bit tough, but yeah, let's have a look. So in our scenario, again, Alice wants to pay Bob an amount of 101 bitcoins. All right, so what Alice possesses is those two transactions which came to her. Transaction A came to her from some other party, and okay, so it happens to be that Alice is a miner herself, and transaction B is a transaction which is a Coinbase transaction, which is a reward for her mining some blocks. So Alice occasionally mined some blocks, so she has got transaction B to herself. Yeah, this is called a Coinbase transaction. Each transaction basically is a set of inputs and outputs. So please pay attention. In Coinbase transactions, an input is just a generation input. It doesn't point to any other prior outputs, as opposed to a regular transaction like A, C, or D, where each input is actually a pointer to a previous output. All right, so that's the main difference between regular transactions and Coinbase transactions, like the orange ones from a few slides before. All right, so Alice has 100 bitcoins from transaction A, which she received from someone, and another 50 bitcoins from mining. So altogether, Alice possesses 150 bitcoins. Now, she wants to transfer 101 bitcoins to Bob. So Alice produces transaction number C, which is actually the same as signing a check, like we saw in the previous slide, and giving the check to Bob. So how transaction C is, what does it have inside? So again, a set of inputs and set of outputs. So each input has to be a pointer to a previous output, unspent output. So in this case, we have one input for which points to output 100. And it's apparently it's not enough because Alice wants to send more. She wants to send 101 bitcoins, so she has to use one more output, which she gets from transaction number B output. So which is this input pointing to this output. You with me? Yeah, cool, okay. So altogether, both those inputs have 150 bitcoins, but she needs to send only 101. So she makes two outputs out of those inputs, one which goes to Bob directly, and the other one is changed. You can think of it of 49 bitcoins, which create a new output and go back to Alice. So this output is actually controlled by Alice. It is Alice's address. This one is Bob's. And then Bob has 101 bitcoins. He can send them to some other guy. So he will create transaction D with input pointing to his 101 unspent bitcoins. He will generate a very simple transaction to some other third party, and that third party will possess those 101 bitcoins. In all this graph, this output is called unspent output. And by the way, it's the only one which is unspent because all others are spent, and they are spent completely. Well, except the change that Alice got. So,
so this actually is also Alice pays Bob and Bob pays someone else.
Yeah, exactly. Okay. So transaction C is is the main transaction from Alice to Bob, and then Bob just transfers those 101 bitcoins to someone else.
And every output is associated with a specific owner?
You can think of it, yes, actually, yes. Every output is every owner can have multiple outputs. Yes. Is it clear enough? Cool, I hope. We'll see in a few more slides. So, as I said before, transaction is basically a set of inputs and outputs. And so this one is a valid transaction, which has 3.5 bitcoins in inputs and 3.4 bitcoins in outputs. The difference between sum of all inputs and sum of all outputs, here it's more than 0, it's 0.1, and it's called transaction fee. What is transaction fee? It's a reward to miners which validate the transaction, and they are collected by the miner which has mined a block containing this transaction. So from this slide, you should take out only the information that there is a notion of transaction fee, which is defined by a simple formula of sum of all inputs minus sum of all outputs. And it goes to a miner. All right?
No. Is the transaction fee fixed or a percentage?
Why I can't go back? What did they do?
How can it be neither?
It's not fee, it's not a percentage, it's just your choice.
Yeah, again. Stay with me, please. Yeah. What was the question?
The question was, is the transaction fee a percentage of what?
No.
So is it fixed?
No, it's not fixed. The question was whether a transaction fee is a percentage of all the amount or is it a fixed amount? No. It's completely defined by the person who creates transaction, by a payer. So if you transfer me bitcoins, you create transaction, you specify your software wallet sums up the inputs.
I'm willing to pay this transaction fee, and
Yeah.
now if this is too low, then I won't validate it. I won't be the miner. That
You're jumping like forward.
Model, right?
What?
It's like a bid model.
bidding.
You can think of it like this, but for now, you should know that you control
The miner.
you the payer. You control the amount of fee that you want to spend. Okay?
Cool. But how do we know who gets the fee? There shouldn't be an output.
You don't know. You don't know who gets the fee.
But it's lost in like
No, the miner collects the fee. You don't know who the miner will be in the future who will validate this transaction.
What's the incentive to pay this?
Later on we'll see, okay?
But is the 0.1, is
Yeah.
there an output like this of 0.1?
No, no, it's not an output.
How can the miner prove that he got the fee?
If there isn't an output.
There should be some mechanism so you can like
How a miner proves that
he got the fee. He owns
he doesn't have to prove anything. He has this transaction. From this transaction, protocol defines that the fee is 0.1.
Transaction itself, that's the proof.
Yeah.
So that's part of the proof.
Exactly.
the aspect.
The perspective.
All right, didn't know that the transaction fee will take so much time. Okay, let's move on. So yeah, all inputs must be used completely. There might be change as we saw previously. So how does a transaction look from inside? So what we see here is a screenshot from a website called blockchain.info. Blockchain.info is a block explorer, is a free website which explores the public Bitcoin, and it gives us a lot of information about transactions, about blocks, and about everything. So what we see here is a main transaction structure. The upper value is actually a transaction hash. By hash, I mean it's SHA-256 cryptographic hash function applied to all the transaction data, and this is the number. Moreover, this is the total inputs, total outputs of the transaction, and the fee. So this particular transaction goes from this input to those two outputs. This is the total output, as we can see here. Few more interesting information can be explored here, but it's not related for now. Just keep in mind that you can find this information on the web. It's completely public, completely free, for every transaction ever created in Bitcoin. And this is actually the Genesis transaction. It is the first transaction ever made back in 2009. And remember the sentence from Times Magazine. So here it is decrypted in Coinbase additional info added in this transaction. The reward from block size of transaction is only 204 bytes. It has absolutely no inputs, and this is the first output where it goes, and it is 50 bitcoins of transaction. All right, so this is how the first transaction looks like. Yeah.
What does the size mean? Like you said, only 204 bytes.
It's the size of transaction.
So transaction from today is also 204 bytes or something like that?
No, it's something like that.
Yeah, of course it's
yeah.
something like that.
It can be a kilobyte, it can be like 5, yeah, but that's approximately the size of transaction. So transaction life cycle. Alice creates a transaction to Bob, so what does it mean? So Alice creates a transaction T. It broadcasts it to its peers in our peer-to-peer network. Eventually, T will get to each node within seconds in all the global blockchain Bitcoin network. Each node, before propagating T, the transaction T, it validates it, meaning it validates the structure, validates inputs, outputs. Signature is validated as well by mainly minor nodes. We'll see in the future what it means, minor.
Validating mean you have to check the whole chain, how it is.
Yeah, so I didn't enter deep enough into what validating means. Basically, there are two types of validation. The first one is like syntactic validation. The transaction is valid syntactically. It has a correct set of inputs, correct set of outputs, and full validation, meaning that there's no double spend, and the amount which is transferred is really possessed by the payer. This type of validation can be validated only by miners. So not everyone is a miner, but whenever miner node gets a transaction, first it validates it like completely, and then it propagates it. So if T is valid, there are two. So first of all, it's added to a transaction pool, some data structure called a transaction pool at each node, and there can be two scenarios. So lucky scenario is where T eventually is added to a block mined by a miner. This answers the question about transaction fees. How should I define transaction fees? Should I make them high or low? So if you make low transaction or low transaction fee or no fee at all when you create your transaction, there's a high chance that no miner will ever want to include your transaction in a block. So eventually your transaction will disappear within some period of time, like a day or something like this, won't be added to any block. If you are shareable enough and you create a transaction with a normal fee or even high fee, a miner will want to include your transaction in a new block, and your transaction will be added to block, added to blockchain, and then it's like stamped transaction happened. Yeah.
So I think I misunderstood. What is validate? I thought this include is the validate. So I'm guessing validate is something different. Right? Each node that gets T validates it.
Yeah.
What happens there?
So the question is what validation of transaction actually means. So as I explained to Avram, there are two basically types of validation. Like this first one is the simple one, is syntactic validation, which is done by each node on the network. But keep in mind that not each node in the network is a miner, meaning it doesn't have all the information about all the transactions. It can't validate it completely. It can't validate the signature. Only miners have the ability, or actually only full nodes. But I'll have a slide on it later on, okay? So eventually T is either added to a new block, which is known as T has one confirmation, or T is never added to any block because of low fees or whatsoever, and eventually it disappears from the network, from every transaction pools of all the nodes, so the sender can resend it with a higher fee. So what we learned from it is the following. When you create a transaction, until it is added to a block, the transaction is not valid. So if you receive a transaction, you have to wait at least one confirmation. Takes approximately 10 minutes now, until you can be sure that it is added to a blockchain and is not disappeared. All right? So next time you receive Bitcoins, wait for 10 minutes.
And the one confirmation
Yeah.
is enough?
Yeah, that's a good question. Is one confirmation enough? So there are two answers. Short answer is yes. Long answer is no. It depends on the amount that you receive. For higher amounts, you should wait for more confirmations. It's advisable to wait for 6 confirmations, basically, in Bitcoin network, meaning an hour. No one does it really, because it takes an hour. So in most cases, one confirmation is enough until you sell a car and receive a huge amount of Bitcoins. So you should wait for 6 confirmations, advisable.
6 confirmations means 6 months?
Means 6 more blocks added to blockchain after a block including your transaction.
And only the first one got the fee?
And yeah, only the first one gets the fee, of course.
So why should they save the other ones that are not getting the fee? Other miners?
Why should other miners what? Include?
Include it in their blocks.
They don't include the transaction in their block. They
Every block validates.
no, wait, okay. So some misunderstanding maybe here. For every transaction, there's only one block which includes it. Okay, other blocks added on top of that block don't include the transaction. They just point back to a block. But we'll have a slide on it later on. Okay, maybe it will be more understandable. So yeah, so before jumping on to a block structure, some some explanation about cryptographic hash functions used in Bitcoin. So there are two of them. One, the mostly used is SHA-256. The other one, RIPMD-160. So for those of you who don't remember what cryptographic hash function is, it basically is a hash function which has two properties. It's a one-way, meaning you can't go back from a hash result back to an input, and it's collision resistant, meaning it's almost impossible to find two different inputs which will hash to the same value. So with these properties in mind, let's go on and explore how block looks like. So we're looking at the block number n. This is the gray area here. It has two parts. It has a header and actual body. So body is simple. It's only a set of transactions. It normally has between few hundreds to few thousands of transactions. The header is actually the more interesting part here. So first of all, header includes a header pointer to a previous block, to block n minus 1. Basically, it's a header hash of previous block. So all this header is hashed. That's the pointer added here. It's 32 bytes of data. Next, we have 12 bytes of some block mining data. I'm not going to cover it. And Merkle tree root, which is 32 bytes as well, making the block header altogether 80 bytes out of whole block space, which is approximately 1 megabyte. So from this slide, you should ask yourself, what the heck Merkle tree root is? And that's actually a good question. So what Merkle tree is, first of all? Merkle tree is a data structure. It is a binary tree, basically, which has an interesting property. So the leaves are transactions. TA, TB, etc. Those are transactions. They are hashed with SHA-256. And those are the actual leaves of the tree itself. So from now on, the tree contains only hashes, only SHA-256s. So first transaction is hashed to HA, transaction B is hashed to HB. Both of them are hashed and produce another hash, hashed together with this guy, produce this one, and all the way up to a root. So what is included in the block header is only a Merkle tree root. So now you might ask yourself, so why do we need it? So there are two reasons. Reason number one is that in order to validate that a transaction is included in a block, it's enough to, First reason is that we want to make sure that no transaction was altered or deleted or removed from a block like a week ago, a year ago. It can't be altered. So think of it, if you take a transaction D and erase it or double the amount over there or make any other change, the hash will be changed, this hash will be changed, and eventually the Merkle tree root will be changed, which will change the entire block header and which will be monitored immediately by all the nodes, and this change will be rejected by the network. Clear for now? All right, so, okay, the reason number two for including Merkle tree roots is to give a fast okay, so the scenario is this. We want to validate whether a specific transaction is included in a specific block. So how we do it? We know the transaction and we know the Merkle tree root. This green thing over here, the path, is called Merkle path, okay, from the actual leaf up until the top. So given a Merkle path and siblings of each layer of the path, we can validate in logarithmic time that a transaction is indeed included in a block. Okay? This technique is not widely used. It's used in sort of wallets called SPV, simplistic verification wallet. So that's the intention behind adding Merkle tree to block headers. Was it clear enough? Well, yeah, data structure, very simple tree. Yeah. All right. So coming up to blockchain itself. So blockchain is actually a public ledger. It's distributed and decentralized data structure. You can think of it as a linked list. Naming each block, as we saw before, has a pointer to a previous block. Each block is added approximately every 10 minutes in a process called mining. Each block size is approximately 1 megabyte. So 6 transactions, 6 confirmations, as we saw earlier, take about 1 hour. Interesting facts. Each block contains sum of transactions created in the past 10 minutes. Because of capacity, it's not a problem actually, it's an issue. Because of capacity issues, there can be multiple transactions, and each block can contain up to a few thousand of them. So not all the transactions are added to the block, only those with the higher fees, actually. Other transactions will wait to new blocks to come, or will be rejected eventually after approximately a day. And so an interesting thing to take out of it is that blockchain does not contain a notion of balance. How many bitcoins does a person possess? How many bitcoins are there in a wallet? How many bitcoins are there in address? All information that blockchain stores is transactions separated to different blocks. All right? So no notion of balance whatsoever in Bitcoin. It's an important fact. So you might ask yourself, so how do I know how many bitcoins I possess? It's actually, this information is presented to you by your wallet software. It's calculated basically. So yeah, so as I said before, it's a distributed, and so in distributed data stores we think of master-master issues. If I have 2 different blockchains, what is the right one? What is the consensus? So the consensus is very simple. The longest blockchain is the winning, meaning the longest blockchain is the true one. So if you have blockchain with, I don't know, 5,000 blocks, and you get another blockchain from some other peer which is longer, so that one is the true one. This is
You mean that 2 blocks are generated at the same time? So
yeah. So there are some issues with it. So what happens when you get few new blocks at the same time? So now you have 2 longest blockchains. So the solution to it is that pretty soon only one of them will be the longest. Like in the next block mined, only one will win, and it will be adopted by the whole network. So simple rule of thumb should.
That transaction validated by one of the blocks that is going to disappear.
Yeah, it will disappear.
How do you know that will stay?
So that's why you try. You are waiting for 6 more confirmations, basically.
Oops.
Yeah. So when you make a transaction in 6 confirmations, 6 new blocks, the longest blockchain will propagate to entire network and will be considered as consensus. It's a bit complicated and tricky. I don't want to dive in too deep into this, but like in a nutshell, that's how it works. So the heart of this consensus mechanism is a proof of work algorithm. This algorithm is actually a mining process, and mining process is applied proof of work algorithm. So in a nutshell, again, what does it mean? So what is the algorithm? So the proof of work algorithm is very simple to explain in a few words. So you have to find some number n such that putting it into SHA-256 will start with some fixed number of zeros. It's like something like 20 leading zeros or something. Okay? Simple, right? That's all. That's all proof of work. So because of properties of SHA-256 and it being cryptographic hash functions, you can't simply find some effective algorithm to find in such an n. You have to guess. So the best way is simply guessing this n. So the more you guess, the more chances you have to find such n that will produce a number with this number of leading zeros. So, and if you think of it, that's a proof of work. If you have an n which SHA-256 really brings you this number of leading zeros, it means that you have invested enough time randomizing and guessing and trying to find this number. And this is proof of work.
How does this connect to validation?
This is not connected to validation. This is called proof of work. Validation happens before. Like, okay, so a good question. The question was, how does proof of work algorithm is connected to validation of transactions, which miners do? So it's not connected. First of all, a miner, when it starts mining a block, meaning finding this n, so it decides on transactions out of its local transaction pool, which will be contained in his block. So he takes, say, 1,000 transactions. He says, okay, those are going to be the transactions that I'm going to include in my newly block. Now, okay, now let's mine a block. Now let's find such n that's to get, well, actually it's a nonce, which is added to a hash of all transactions, okay? So let's find such nonce that the output will, of SHA-256 will start with a fixed number of leading zeros. When I find it, all those transactions are added to the block, and that's the proof of work algorithm, actually. Yeah, I have many questions now.
Like, okay, I proved I've done some work. Maybe there's other proofs that I ran 10 miles. Okay? How this makes me credible to validate these transactions? How, why am I more
No, okay, yeah.
Why am I more credible than others?
Yeah, you are right. So you are not credible. You, as a miner, can cheat, meaning you can include transactions to yourself or like change transactions or stuff. So whenever you you mine a block, you propagate it to all the network, and all the network, of course, validates the block and all the transactions inside that block. Okay. This happens. There's a slide explaining it. Okay. In more details, this slide actually describes the proof of work itself. How it is connected to validating, I'll explain in a few more slides. Yeah.
What are the requirements for n? Like,
Yeah.
if I found n and do this work, why you cannot just reuse it next time? Like, I need to find every time new n.
Yeah. Okay. So good question. So if I found an n, why? So okay. So actually, you are not finding. I cheated here a bit. It's not an n. The number which is hashed, it's a nonce, together with the hashes of all the transactions that you chose to include. But yeah, I wanted to keep it like in a nutshell way and just explain the basic stuff. But yeah, of course, yeah. All right, so again to blockchain.info website, to Blockchain Explorer. So that's how block number 500,000 looks like. a lot of info over here. So this particular block contains 2,701 transactions. What interesting, it has a pointer to previous block. It has its own head hash. Block reward, it's 12.5 bitcoins to a miner which revealed this block. This is Genesis block number 0. It has only one transaction. This is the transaction. We saw it previously, by the way. And pay attention, it has no previous block, so it's all zeros. So this is the number 1 blockchain with reward of 15 bitcoins. 50. And by the way, Alex, this is the nonce. This is the N, actually, okay? Which produced the first proof of work result. Yeah. Okay, so that was like the hardest part and the longest one. Now let's go to Bitcoin network, how it's constructed. So first of all, it's a peer-to-peer over TCP. All nodes, also known as peers or clients, are equal. There's no hierarchy of nodes. All the transaction is public. It's not encrypted, it's not signed, it's completely public. And each node has one of 4 roles. So first of all, each node is a routing node, meaning it passes the data on the net. Node which has a full blockchain on it, data structure which is now currently approximately 170 gigabytes of data. So a node which has full blockchain is called full node, and this is a term. Some nodes have wallet capabilities. We'll see in a few more slides what wallet means. Not every node has to be a wallet. And of course, miner. Not all nodes are miners, but a miner should be a full blockchain node as well, because it has to validate all the transactions. So, so the two main data structures passed on the network. This is network. Hello, this is a Bitcoin. And those nodes is a subset of nodes of Bitcoin. So 2 main data structures transferred are transactions and blocks. So we'll have a look. For example, node N. Okay, green ones are simple nodes, meaning they are routing nodes. Red ones are full nodes, and we have one miner node over here. So we start with new transaction created by this green big guy. It creates a transaction. Remember, it creates a check and signs it. Now it propagates it to the entire network by propagating it first to its peers. Then they validate it. Full blockchains and miners, those 3 guys validate it fully. By fully, I mean they validate the transaction is not a double spend, and that N possesses the resources, the needed Bitcoin inputs, and they are unspent. Those guys, those 1, 2, and 3 green guys don't have this capability because they don't have full blockchain on them, so they only validate the transaction syntactically. When the validation completes, they pass it to their peers, and that's how transaction propagates in a matter of seconds to the entire network. Okay, so and the other thing, the other data structure is block, of course, which is mined by a miner. It includes transactions and proof of work made to it. When miner creates a new block, it sends it to its peers. Each peer validates that the block is structured correctly. If so, it propagates it to its peers and so on, and only full nodes keep the new block to themselves, adding it to a blockchain. Yeah, okay, so that was a quick one. Now, okay, I think I have 5 more minutes, and last topic, which is keys, addresses, and wallets. So this schema actually summarizes the whole topic, but yeah, let's dive in a bit. So in Bitcoin, everything starts with generating a private key. Private key is 256 bits random, pseudo-randomly generated number. Then applying elliptic curve manipulation. What does it mean? Who knows here what elliptic curve is? Please raise your hand. Okay, 3 people. Cool. Okay, so never mind. But like few words about elliptic curve. It's like a modern way to make cryptographic signing, basically. Okay, by algorithm called ECDSA, elliptic curve digital signature algorithm. So it's like a standard way, not used only by Bitcoins. You can Google it, but just keep in mind that this exists. Applying this algorithm, we generate a public key, which is 257 bits. Up until now, it's very straightforward. The interesting part starts from public key to Bitcoin address, which is only 200 bits. So this is how it works. So we have a public key created by elliptic curve multiplication. We take it and pass it through a process which is called double hash, which first passes through SHA-256, then RIP-MD160. We get an output of 160 bits here, and this is public key hash. So keep in mind that from here we cannot go back, right? It's one way because those are cryptographic hash functions. From public key hash, we apply base 54 check and code algorithm and create Bitcoin address. So what it is, it's internal Bitcoin algorithm. It's public, right? It uses base 58, not base 64, which is well known. We'll see in next slide why. So basically, what's the important thing here is Bitcoin address. This is the thing that you are using when you send in Bitcoins. This is the address that you put in your check transaction. So example, this is Bitcoin address, standard Bitcoin address. It always starts with leading 1. And keep in mind, because of base 58 encoding, it does not have capital O's or zeros, or capital I's and L's and lowercase l's, in order to avoid ambiguity. Okay, so every address won't have those 4 letters, actually 6, yeah, to avoid ambiguity. So why do we need, so I'm going back to this slide. So we have public key and we have public hash, which should be enough actually. Why are we creating Bitcoin address itself? Sorry, we have a public key. Why shouldn't we just use public key instead of Bitcoin address? Why do we need all this algorithm to produce Bitcoin address? Why public key is not enough? So few answers are here. First of all, Bitcoin addresses are much shorter. They are much more readable because they all start with leading 1. They don't have ambiguous characters. There's also a checksum included in Bitcoin address, which can validate that it was really structured well. Yeah, but it's not like convincing enough. So, and actually the answer is unclear. So rumors say that Satoshi Nakamoto, when he invented whole system, thought that there might be a potential exploit in elliptic curve digital signature algorithm, meaning when you have a public key, you might, in some future time, exploit it in a way that you get the private key. And well, when you have a private key, you are the owner of all the Bitcoins. So The rumor says that he was afraid of this future exploit mainly because elliptic curve, the ECDSA was, though it was invented back in 1985, it was coming to wide use only in 2005, only 3 years before Bitcoin creation. So with that in mind, Satoshi Nakamoto added all the hashing algorithm, all the double hashing to public keys and introduced Bitcoin address. So possessing Bitcoin address, you can't go back to public key. Clear enough? Okay, so yeah, so now the final thing is Bitcoin wallets. So Bitcoin wallet is actually software, hardware, or device which manages, so most basic function is managing keys. All of you guys have those papers, so what those papers are? Those are valid Bitcoin paper wallets. All they have Bitcoin address and private key. So if you want to use, they are all the same. So don't use it to send in Bitcoins because all of you possess the private key. It's shared between all of you. So, but you can generate them freely and print them. Private key should be only yours. You should store it in a safe, in a wallet, like physical wallet, whenever you need. And Bitcoin address is the one you use to receive Bitcoins from your peers. So I'm wrapping up. So main Bitcoin wallets functionalities is key storage, creating new addresses. A very important thing is ability to import, export, and backup of all your addresses and keys. The common practice used is creating a new address for each transaction that you receive for your privacy, basically. It's not required, but it's commonly used. So more sophisticated wallets, other than those of these papers which you have, of course, use the functionality of sending and receiving Bitcoins and setting transaction fees, which you as a user might choose which fee you put. And so the wallet software will show you your balance. Because as we said before, blockchain does not know any notion of balance. Balance is calculated by your software wallet. It's not important, so few known wallets out there, not important. Yeah, those two guys are actually interesting, very cool. These are hardware wallets, which are also known as cold storage wallets. Two out there, like Trezor and Ledger Nano. Until they are connected to the internet, all Bitcoin stored inside, meaning all keys stored inside are completely safe. So people which tend to have a lot of Bitcoins tend to buy those devices and keep them in a bank safe or wherever. So yeah, this is actually the final slide. So if you choose to enter the world of Bitcoin and start accepting Bitcoins and sending Bitcoins, you'll have to pick some wallet. It should be nice and easy to use, but the three main guidelines you should consider are: it should be open source, it must be open source, it must guarantee that you are the only owner of private keys kept there, meaning they are not backed up or copied in some server or share them on I don't know whoever it might be. And Bitcoin wallet should have a backup ability, sorry. So use wisely. That's all for now, folks. Any questions? Yeah. Yeah, I understood completely the entire Bitcoin. Cool.
We're just mining already.
Started mining. Yeah, cool. Well, thank you very much.
Thank you very much, Dima, for addressing this non-simple topic. And okay, for the next activity, we'll have a 5-minute